This shows the amplitude modulation being sensed by a sensor on phase 2. We have all three phases being loaded down by inductors. When in fact we try to load all three phases with inductors down, we encounter a problem in that we get a good arrangement with just two secondaries on one side of the 666 primary system. When we add the third secondary to that side, it considerably reduces the amount of current that all three secondaries will see. And so as an attempt to remedy that situation, what we do now is that bottom, here's the sensoring coil. This sensoring coil here is picking up the AM modulation underneath channel 2, the blue. We have high induction coil sensors also being added, of which one is scope monitored. That tells us our secondary voltage in relation to that, and that's channel 2 of the thicker middle signal. Let me look here back in the background then. The original flat geometry of the 666 coil system has been altered so as to contain two top coils and one bottom coil underneath that one there. That represents our phase 3. It's on the other side, the capacitor connection side of that phase. Now once again, now we have three coils to work with that are generally are producing generally equal currents in space. As for their currents, the top scope monitored coil, which will go and show that. See the scope leads right on there. If we pick that coil up in the vicinity with our scoping, you ought to be able to see channel 2 change. Do that one more time. I think here we're synced on one signal, so that's why the signal goes out when we're out of vicinity. But this is a good opportunity to see our wattage, and we'll conclude with that. This is a very special signal. We can say that our power input is being heterodyned into all of these coils, going down and up in certain cyclage, probably 19 cycles per second. Okay, then to conclude, why this camera's being on me. We have 1 volt inputs. The phase amperages appear to have gone out. We have phase 1 showing 1.1 volts with a apparent power of 0.11. That's that meter right there. It's secondary. One in front of us is producing 15.6 milliamps. That's at 140 ohms resistance. Looks like stable amperage input on the secondaries as we see on the scopes. The scope does not indicate a great pulsation. So we've got a steady 15.6 milliamps on 140 ohms on phase 1 for a cost of 1.1 volts times 0.11 amps. Phase 2 got 1.1 volts inputting 0.076 amps in a cyclic manner. And phase 2 is the back coil. The back coil. The amperage meter has gone out. $18.7 milliamps on 140 ohm high induction coil. And thirdly, we have phase 3 inputting 1 volt at 0.145 amps, and on its secondary achieving 18.9. It's fluctuating amperage, 18.8, 18.7, 19. And so that will conclude that. From that information, we can fathom what the power factor of the device is on that direct power transfer, and then deduce how much to take off to account for the pulsing of that power. Now here shows the phase angle that we normally would use to procure 280 volts from the device with just 2 coils. Adding the 3rd coil has decreased the efficiency of that voltage generation, or it's increased the phase angle, one of the two. And we'll call that quits then for this demo. Take the last shot with this unusual amplitude modulation pulsing. Evident as a power input. Even though the bottom and top amplitude may be only 1/3 of a total in difference, when this translates into actual power transfer, that becomes an exponential relationship near 9:1. So you're actually conveying 9 times more energy at the peak of that pulse than you are at the bottom. That leaves significant areas of time where the expected power input to achieve that stable secondary voltage, which is the center one. Well, you all get the idea. That's it for now.